this assessment asks us to explain the large difference in chemical shift for HA and HB. Now, what's interesting about this one is that usually two hydrogens on the same alkene are going to be right around the same chemical shift, but here we see a big difference between the two. The difference in chemical shift can be attributed to the electronic environment of the two hydrogens. And so one of the things we might think about with HA and HB is we notice that HA is a little bit closer to the ketone, and so we might imagine some inductive argument. But let's look at another argument that we can make instead, and that's to look at resonance. And so we can draw a resonance structure where we move the electrons in the CO pi bond onto oxygen to generate the resonance structure shown here. We'll put HA and HB still in the molecule. Now, having drawn this resonance structure, we have another CC pi bond that we can draw, an extra one, where we move these pi electrons to this carbon here to form a new double bond here. And so that gives us this structure, where we now have a positive charge on the carbon that also bears HB. And so looking at these three resonance structures of this cyclopentenone, what you notice is that in this structure here, HB is attached to a carbon that has a positive charge, a very electron deficient carbon. As a result, we're going to expect to see HB at a higher chemical shift. Notice in drawing these resonance structures, the carbon that has HA never gets the positive charge. As a result, HA is going to be at a lower chemical shift. Essentially, the answer to the question then is the fact that we can draw resonance structures that puts a positive charge on the carbon with HB, but we can't do the same at the carbon with HA, means that the electronic environment for HB and HA are significantly different. This results in a big difference in chemical shift. And by big, around 1 part per million. So on the NMR scale, that's a big difference, but still just 1 part per million.